Hey math people, welcome. So in this video, we are going to work with the following system of two linear equations. The first equation is 3x1 minus 2x2 plus x3 is equal to 0. And the second equation is minus 6x1 plus 4x2 minus 2x3 is equal to 0. So we have a system of two linear equations with three variables x1, x2, and x3. And notice this is a homogeneous system since on the right side our constants are equal to 0 for both of those equations. So if we want to go through our systematic way of finding solutions for this system of two linear equations, we set up our augmented matrix. So the top row has all of the constants from the top equation, including the right side. And so the top row of this matrix is 3, minus 2, 1, 0. And the second row of this matrix is minus 6, 4, minus 2, and 0. So we have our augmented matrix. I've got a pivot right here. So I'm going to eliminate the entry below by multiplying row 1 by 2 and adding it to row 2. And that will eliminate every single value in row 2. Since row 2, every element in row 2, right, is exactly minus 2 times the same value right above it in row 1. So what we can see here is that this system is actually just one equation written 2 times over, right? The solution to this equation is exactly the same as this equation since we've just multiplied this equation, both sides of it, by minus 2. And so to continue and writing this in reduced row echelon form means we just need to scale row 1 by 1/3. So I divide everything in row 1 by 3, and this gives me a top row of 1 minus 2/3, 1/3, 0. So here's the reduced row echelon form. And so I have a basic variable for x1 because I have a pivot here, but now I've got x2 is a free variable and x3 is a free variable. So in this case, we have two free variables, x2 and x3. So we are going to have an infinite number of solutions. We have more than just the trivial solution here. And we can write this out similar to the way we worked with the previous example. This top equation over here is telling me x1 minus 2/3 x2 plus 1/3 x3 is equal to 0. And when we write out these solutions, we usually solve for the basic variable. So in this process, we can rewrite this as x1 is equal to 2/3 x2 minus 1/3 x3 when we bring the free variables to the other side. And x2 and x3 are free. So I can write this in a similar matrix form by factoring out the x2 and the x3. So I can write this as a sum of two vectors. The first being 2/3, 1, 0 times x2 because I have 2/3 times x2 over here. I have 1 times x2 over here, and I have no x2 over there. So that's why I have a 0 holding that place. Plus all of the x3 stuff. So for the x3s, I have a minus 1/3 up top. There is no x3 for the x2 equation, so I put a 0 there to hold that place. And down here, I just have 1x3. So I can think of this as some number times this vector plus some other number times that vector. So we can write this as a vector equation, x2 times the vector u, where here's the vector u, plus x3 times the vector v. And so here is the vector v. So in our case, vector u is 2/3, 1, 0, and vector v is minus 1/3, 0, 1. And so what would this solution set look like? Well, recall from our previous example that if we have one free variable, if our solution set has one free variable, then we got something like some scalar times a vector v. And so that gave us an entire line of solutions. Anything that is parallel to the vector v would be a solution. So when we have one free variable, we have an infinite number of solutions that sit on the same line. In this case, where we have two free variables, x2 and x3, we can get, well, I can represent u as a vector. I'm not quite drawing it in the right direction over there. Vector v is some other vector which is not parallel to it. And then we're multiplying u and v by scalars. So what we're actually getting is an entire plane of solutions. So anything that sits in the plane that's spanned by the vectors u and v is going to be a solution. So when we have two free variables, we get an infinite number of solutions, and those solutions sit in the same plane. So we get an entire plane of solutions, and we can write the equation for this plane as 3x1 minus 2x2 plus x3 is equal to 0. So we've discussed different ways that we can represent solution sets to systems of linear equations. So I just want to summarize those different ways on the next slide. So for this homogeneous system of two linear equations, 3x1 minus 2x2 plus x3 is 0, and minus 6x1 plus 4x2 minus 2x3 equals 0. Below are four common ways that we can represent the solution set to this system of two linear equations. So the implicit solution, for example, one way to give that would be to just use the equation, the top equation for the plane. So an implicit solution would be the plane 3x1 minus 2x2 plus x3 is equal to 0. Note that we could have just chosen the second equation in this system as our implicit solution. So an implicit solution is not unique, though they should be equivalent equations. For the explicit solution, oftentimes if I want to solve for x1, rather than have the x1 jumbled up in the equation, it's nice to say, well, if you know what x2 and x3 are, here is how you could figure out what x1 is. So the explicit solution would be what we get when we take the implicit solution and solve for x1. So the explicit solution here would be x1 is equal to 2/3 x2 minus 1/3 x1. And so now this is a unique solution. The explicit solution should just have this one form. On the previous slide, we expressed this same solution in vector form. So what I mean by that is we wrote it as x2 times the vector u, which was 2/3 1 0, plus x3 times the vector v, which is minus 1/3 0 1. So the vector form of this solution we could write as x2 times the vector u plus x3 times the vector v. And so one additional way that we can represent this solution would be what's called a parametric vector form. So the only difference with parametric vector form is we just denote these values x2 and x3 with arbitrary constants. We parameterize them using variables s and t. So here, rather than use x2, we're going to say that the solution has the form some constant s times 2/3 1 0 plus some other number t times the vector minus 1/3 0 1. So we can write this as s times the vector u plus t times this vector v, where s and t are real numbers, are scalars. So the only difference is we change this x2 to an s, we change this x3 to a t. And this is what we would call the parametric vector form of the solution.